Welcome, ladies and gentlemen, to the technical forum here on the group exhibit Hydrogen Fuel Cells and Batteries. We have wonderful exhibitors here. One of them you can see just over there, Dexmet Corporation, expanded metal foils for next generation power applications. And we will have a presentation now from Dexmet. We will hear a value proposition for microgrid expanded metal foil from John Hart, Business Development of Dexmet Corporation from Connecticut in the United States. Looking forward to your presentation, John.
All right, thank you. As it states, I'm going to be talking about the value that we believe microgrid expanded metal can bring to lithium-ion battery developments. We've been in business for about 60 years now, and we've got quite a global presence in different areas. Our material is used today in primary batteries and in lithium polymer batteries, but as far as we know, nobody in the industry is using porous mesh foil for lithium-ion batteries. So that's what we're going to be discussing today. What you see here is a representation of the different components and materials that go into a lithium-ion battery. And if you notice, the green is where all the value is. That's the electrode material, both the anode and the cathode. Everything else in yellow, the container, the electrolyte, the anode current collector, the cathode, the separator, all of that is a cost. It's a necessary cost and can be looked at as potentially a necessary evil in the battery in that you have to have it, but it creates a cost and a weight burden on the overall value, which is in the electrode material. So what I want to talk about is why expanded metal foil will contribute more to the value of the anode material and the cathode material. Just to give you a little background on the company, as I'd mentioned, we've been in business since 1948. We've got a global presence in that time. Our primary markets have been legacy for primary batteries and lithium polymer batteries, but we also have been, for the past 20 years or more, providing materials for fuel cell development. It's used both as a low-cost substrate for platinum deposit for the catalyzer. It's used as a flow field for electrolyzers, and it's used as a support for graphite conductive material in a high pressure area. It'll provide the stability for it. We also do a great deal of business in lightning strike protection. About 70% of commercial aircraft composite materials embed our material into them for lightning strike protection. Now, the process is pretty straightforward on how we make the foil. We basically have very precise micro tooling that if you blow it up, it would look like a saw blade. And what we do is we basically slice into the solid foil, we make cuts, and the depth of the cut dictates the width of the opening. The feed rate will dictate the thickness of the different strands, and the angle of the injection will dictate somewhat the depth of the pour. So by controlling those three aspects, we can make literally thousands of different configurations here and customize those for each one of our individual customers. So what we do is we have an inventory of samples that we work from. And when a customer wants to try and get some material from us, we try to identify something that would be a close fit for what their application is, and we'll send them a sample. And then as they work with it, we work with them to develop the contour and the design that would be optimizing for their particular application. Now, for lithium-ion batteries, we've been in development for the past 5 years developing the micro tooling so that we could get down to where we could create this kind of foil on a 25 micron. And so we've developed samples where the copper foil at 25 micron is 58% open area, which is the weight equivalent to a 10 micron solid copper foil, which is the industry standard. On the aluminum side, we've made samples of 51% open area, which has the consistent weight burden that you would get from a 12.5 micron aluminum, which again is consistent with industry standard. And if you're interested, we have plenty of samples right behind you at the booth there. one of the primary causes of battery failure is delamination at the bonding of the electrode material with the foil. So I've made this representation to try and show you what that means. Is when you're depositing the electrode on both sides of the foil, there's a dynamics that goes on during the cell when it's charging and recharging during that cycling process, and you can almost think of it as a mild amount of breathing in there. There's some movement going on in there as the ions are moving back and forth in transition. And over time, that starts to degrade from the bonding on the surface here, and you start getting delamination, which over time will kill the battery. The point we're trying to make here is with porous foil, we've got over 1,800 pores per square inch in that foil. It's more than 50% open area, so that you've got a strong bond between the different areas to hold that foil to both sides, and therefore we believe that that's going to, the indications we're getting from cycle life is that this has a great deal to do with extending the cycle life of the battery. This is a blow-up of what the electrode material looks like on a solid foil. So if you look at this, there's two types of binders that are necessary to hold the electrode together. One type of binder binds all the different particles together and holds it together similar to what butter does in a cookie. When you bake it, it holds everything together and keeps it in place. The other type of binder is used to adhese to the solid surface down here. But if you look under this SEM photo here, in a very close-up, you've got less than 50% of the electrode material actually making contact with that foil. So it requires a pretty aggressive binder to adhere to this and maintain the cycle life without breaking that apart. So anything you can do to reduce the amount of binder in here, which is a cost to the battery, and eliminate the weight that that binder causes, is a good thing. So I've put this together myself here. You can see it's made of a composite of a bunch of pictures sliced off of here. But it kind of gives you a visual of the difference. And I think you can clearly see that by having this chemical bond across here is going to be much, much stronger for holding this together than if you're just trying to adhere to about 50% of the surface here. In doing so, you reduce the amount of binder that you need to devote to holding it to that foil, and therefore you're reducing some of the weight out of the battery, which all contributes to the value that you have in that battery. The rest of the slides I'm going to be showing you here are some of the feedback we've gotten. We do not do our own R&D. We've been sending samples out to institutions and universities and developers around the world for the past year, and we're starting to get feedback from some of the people who've been working with our material. And it's been showing us some pretty indicative results of where we think there's some great potential with what we have. This was done at Wayne State University in Detroit, Michigan, by a group called Frontier Applied Sciences. They've been working on developing silicon anode, and this is, grant you, on a coin cell, so it's a one-layer cell. But what they did is they replicated their control group, which was the basic unit they were using, and they simply substituted our expanded metal foil for the solid foil to just see what the difference was. And as you can see, it's an extremely profound difference. With the expanded metal foil, after 35 cycles, we've still got more than 80% capacity, where in their control, they dropped to 80% after about the 5th or 6th cycle. So this is coin cell R&D work, but it's still very indicative of the potential that expanded foil can offer. Here, this is an example from a third-party developer who, because they're a developer, they prefer to remain anonymous, but they do share their data with us. And as you can see here, they were working on a lithium-plated anode. And again, what they did is they maintained the control as their usual anode-cathode development, and they simply substituted the expanded metal foil for the solid foil on the anode. And you can see after 41, and this was done on a pouch cell. So it was a one-layer pouch cell. This is R&D. But you can see after 42 cycles, they've got 186% greater capacity simply by exchanging the expanded metal foil for the solid foil. And if you take that out further, you can see that the cycle life is extremely extended by having expanded metal foil in here. If you extrapolate this out, they're probably going to get out to 200 cycles before you drop down to 0 here. Now, these next two slides were part of a paper that was done by Ningbo Institute in China. And they're working with NMC and graphite. And the same principle, they took our expanded metal foil, did everything exactly the same in their cell development. This is, again, a caution, it's a one-layer cell, but it's a pouch cell. And they did everything identical in both sides. The only thing they did was exchange the expanded foil for the solid foil. And they did it in 4 variations: solid, 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 expanded, expanded, solid, and then expanded, expanded. And to cut to the chase, if you look at where they used solid foil on both anode and cathode and used expanded foil on both anode and cathode, they doubled the available capacity. And also you can see, again, there's a significant extension in potential cycle life here. Just back up here a second. On this study, you'll note this was done at 1/2 C discharge rate. This study was done at 5 C discharge rate. And this study at Ningbo was done at 10 C discharge rate with the same results, more than 200% available capacity using expanded metal on both the anode and cathode. So even though this is R&D, it's one-layer cells, coin cells, and pouch cells, it has demonstrated significant, profound advantages, potential advantages, by using expanded metal. What this has led to is it's prompted a lot of the major battery companies around the world to start taking an interest in this. And we're sending out rolls of our foil now to several different companies who are going to be doing full prototype coating, creating full multi-layer cells. And we hope within the next 3 to 6 months to have some very meaningful data on real-world batteries that we can share. Another cause of battery life is capacity fade. And capacity fade is a result of, during the overcharge, over-discharge cycling process, you get decomposition somewhere in the cell. And you get either film formation or material dissolution or other types of degradation in the cell. Now, what I'm trying to represent here is in your today's cells where you're using solid foil, you've got solid foil in each layer. And so in a cell, what you really have is a bunch of cells combined to make one big cell, because there's no communication between these individual layers. So if you get degradation in one layer, that's going to drive down the capacity of the whole cell. With porous material, in theory, we don't have any proven data for this, but in theory, you've got complete saturation throughout that entire cell between each one of the individual layers, so that if you do suffer some level of degradation, you've got more available active ions and electrolyte material to cover for that. So we feel that in some of the studies that we're doing with people right now, we're going to be able to demonstrate a reduction in capacity fade. On the production side of things, we've been working with a company, Megtech, which makes automated coaters. And we brought some material to their facility, and they had it set up with a vertical coater. So the solid foil is coming over the top, and they're coating the underside of that foil here. Then what you would have to do is come back around and have another coating injection coating the other surface. So what we did is by threading our material through there in one pass, they were able to, as they're injecting, the slurry would go through those pores and actually deposit on both sides of the foil. This was not a 50-50 balance. This was a prototype example to just show the proof of concept, but they feel with enough tweaking that they can get this dialed into where they can probably get very close to a 50-50 balance on both sides. And at the same time, because it's 50% porous, we feel that even if it's not a complete 50-50 balance, maybe a 45-55, you've got 50% open area, so the foil itself should be somewhat seamless within that. It should be rather invisible to the foil. If you calendar it down and you've got a good calendaring on there, if you're off a little bit in the foil, we don't know for sure yet, but we don't feel that that's going to have a major impact on the results you get from that cell. So this could potentially drive down the cost of production. Another cost driver in cell production is the wetting and aging process and degassing. And when I've talked to people who are doing this, they say they sometimes leave the cells after they inject the electrolyte. They'll even sit for 12 hours, 24 hours. And I've been told that that is a significant logjam in the process of developing cells. And again, the theory is that we feel that because our material is porous, the ability to wet this material can, if we start to measure this, we can probably determine that we can reduce the amount of wetting time that's necessary by a significant amount. And again, this is looked at as another cost savings. So to summarize all of these cost savings, what we're looking at is the potential to significantly increase available capacity, significantly reduce delamination, increasing cycle life, reducing capacity fade, reducing soaking time, and also reducing the amount of coating time. So if you add all that up, we feel that there is a very profound amount of potential cost savings during the battery development process. Now, a few weeks ago, we were at a exhibition called International Battery in the U.S., and we were asked by the U.S. Automotive Battery Consortium, who was very intrigued by this, to put together a proposal for them, because what they want us to do is start to work with one of the battery companies that we're already engaged with, and we're going to write a protocol so that we can actually quantify each one of these savings, because the automotive industry wants to know, is this all sounds well and good, but how does this interpret into dollars? So we're going to be doing a project over the next year where we're going to be evaluating each one of these segments to try and put an actual dollar value to this so we can see what this is going to amount to. So the one question everybody always has in any business you're in is, how much is it going to cost? We are still in R&D, so we don't know what it's going to cost. The tooling that we've made, the micro tooling that we use, was designed, but we're using it on a machine that was not designed to work with 25 micron foil. We have to do some more R&D as we develop a more greater interest in our process for this industry. We're going to be devoting more time to developing our technology and developing the equipment we can so that we can be mass producing this material for people. And right now I'd be hesitant to put a value on it, but I think we are very confident that by looking at all of these value-added cost savings, we're going to very easily be able to demonstrate its viability. And again, I'll just go back up to this one slide. This is what a battery is, and the value of the battery is in the green, in the electrode material. It's all about the electrode. All the rest of this is a cost, but if you have something in here that may be an additional cost but increases the value, then I think we've got something that'll be very interesting for the market. And that's what we're working on. Is this next year we're going to be making full cells that are representative of actual industry used standards, and we hope to have some better information for you here in the next few months. Thank you.
Thank you very much, John. Here's your applause.
Oh, okay.
I think an excellent presentation, cutting down the cost by the half. That's really something, you know, you can really be proud of it. So are there any questions from your side? Just raise your hand. We'll be with the microphone right with you. If you please introduce yourself.
Fauzi from Saudi Arabia, Rabi Electric. How long does this technology will take to materialize and start getting the real benefit of renewable energy? Because energy storage is one of the key burden for the renewable energy.
With regards to developing the foil, we have the tooling that, back up a little bit, when we were developing materials for lithium polymer and for primary batteries, the thickness was around 75 micron foil, because they're packing in material into that foil, and usually they're making bobbin one layer cells. We found out that about 10 years ago that lithium ion was going to be pushing for thinner and thinner. So we spent 5 years developing the tooling. The challenge for us now is we need to next design the machine so that we can more aggressively automate our technology and develop it so that we can make it in mass production. Right now we're in prototype phase. We can run it and make this foil, but in a very limited quantity, and it's just samples. So we need to refine the tooling. To answer your question with a timeline, I would say we could be there within a year or two. And that'll be following very closely with the market, because the market right now, we can produce enough for prototypes. We can produce this thousands of meters of material right now for prototype applications, and we feel that as people get into the hundreds of thousands of meters, we'll be there.
That's good to hear. Any more questions from your side? Not at the moment, so I would like to invite everybody of you to visit John at his booth with Dexmet, expanded metal foils for next generation power applications, and ask further questions over there. Thank you very much, John.
Thank you.
Thank you. It was a pleasure. I am sorry to tell you that the next presentation about virtual training models for technical training, the No-High project, won't happen here on stage, but the next presentation will be at 4 o'clock, in situ characterization of single cells and their components, presented by Ulf Groß, Head of Department Fuel Cell System of Fraunhofer Institute for Solar Energy Systems. So be again here at 4 o'clock. Thank you very much.